So part two of the aqueous ions in solution covered quite a lot last time when we looked at the acidity of metal 2, metal 3 aqua ions. Noted that metal 3 hexaaqua ions are more acidic. That's going to be relevant today. And then we spent a bit of time looking at copper 2 and iron 2 hexaquas reacting with hydroxide, ammonia and carbonate. Basically the same routine again, but this time we're looking at iron 3 hexaqua, which is pictured there, and aluminium hexaqua as well. So here we go. Now, as we just said then, those are our two aqueous ions. Just realise that square brackets superscript, but you get the idea. It should be full like the other side. Same three bases as before, hydroxide, ammonia and carbonate. Sensible source of hydroxide would be NaOH. Sensible source of carbonate would be sodium carbonate, Na2CO3. And ammonia is a gas at room temperature. That's not what we're using here. This would be aqueous ammonia, which is alkaline, as we discussed in the previous lesson. Pay attention to all the equations, make sure you can write them for yourself, make sure you can draw these structures, make sure that you're aware of what the colour changes are and the observations that should be made. Let's get going. Now, this is a species that we have mentioned its appearance of before. However, it was mentioned in passing when we looked at redox titrations, and there wasn't a huge amount done about it. What colour is hexaaqua iron 3? I wonder if anyone's picked it up and remembered it. Well, the answer is it's that colour. And so therefore, well, we describe that as purple, according to AQA, or traditionally, or for my sort of, when I was learning it, we'd call it violet. It's pure, when it's like the hexaaqua, like actually what you can see there, that complex structure on the left, then it's that colour. However, very often it actually appears brown or yellow. We'll think about why a little bit later. It's to do with hydrolysis, which means some of those waters breaking off when they react with other waters. We'll come to it in a bit, you'll see. And what about aluminium? Well, there's aluminium 3 hexaaqua. Aluminium's not a transition metal. Can I just remind you of that? It's in the P block. However, it's been thrown into this, so we're not really in the transition metals topic anymore. We're just talking about metal ions in general. We've got aluminium. What colour would you expect aluminium anything to be in solution? It's not a transition metal. Well, the answer is colourless. It's not true to say that the only colourful chemicals are transition metal compounds. That's nonsense. However, most metal species, if they're not transition metals, are just colourless solutions and white solids. There are examples that go contrary to that. So like lead iodide. Lead's also in the P block, so it can't be a transition metal. Lead iodide's bright yellow. There are some exceptions, but generally speaking, if it's in group 1, 2, or if it's aluminium, it's colourless in solution and it's a white solid. That's good for us because that means that all of the aluminium compounds today are going to be colourless or white. And we can tell if it's going to be a solid or not because it doesn't have a charge. Do you remember that from last lesson? And so it'll be a white solid. And if it does have a charge, it'll be a colourless solution. That makes things quite easy for us. Let's have a look then. So we'll start with iron 3 hexaaqua. We'll look at it reacting with hydroxide, and then we'll also look at it reacting with ammonia. Get that done. Then do the same for aluminium, and then we'll look at the carbonates together. So what we get here is that standard Larry-Bronsted acid-base reaction that we saw last lesson. So how about you write the equation for this before I reveal it? So pause the video. In case you're not sure what to do, I'm asking you to write the hexaaqua iron 3 plus some hydroxides makes what you think it should make plus product. It follows the same pattern as before. Just note this is a 3 plus ion. In case you're waiting for the answer, there it is. So yeah, same as before, we've got this time 3 pluses, which means 3 H pluses can be lost before it ends up as this uncharged species, which then precipitates out of solution because it's not soluble or as soluble as when it's charged. And so that's the sort of end of it. That's what we get. So hopefully you can see that. Now, observations. We said that our iron 3 hexaaqua is purple if it's properly hexaaqua. Oh, go on then. Who wants to have a guess? I'm hoping that you're guessing at home or wherever you're working. This species here, this iron 3 hydroxide species, I'm going to call it, but really it's tris aqua, tris hydroxy, iron 3. Well, there's its structure. You can see that there are 3 OHs. There could have been any 3 OHs, by the way. I just picked those 3 almost random when I drew that structure. No charge. Colour? Well, we're looking at the precipitate there. So this, because it doesn't have a charge, would be a precipitate. Don't worry about the fact it appears to be floating. That's not necessarily the case. It's rusty coloured. It's iron 3 hydroxide. Hydrated iron oxide is rust. This is similar to that. It's not rust, but it's rusty coloured. You can see the similarity. It's also iron 3. Okay, good. Now, you might be wondering, okay, that's what the precipitate is, but how come the solution underneath it is yellow? This is a bit of extra, but I want to really clarify this. That solution there will be the intermediate acid-base products. Remember what we did when we looked at copper 2 hexaaqua in the previous video? We started off with it as 2 steps. Gives off 1 H+, makes a water, loses a positive charge, and then in the second step the next. And then we summarized it by putting them together. I won't labour it now, I won't make you watch me go through it all, but this is actually 3 acid-base equations. It's that loses a H, so you get 5 waters, 1 hydroxide, as the product, and 1 water, and then the same again, and the same again. Those species there are the intermediate species. That's having lost 1 H+ and a second H+, and then finally it goes, loses its third H+, and we end up with this uncharged species. They're both yellow. Now, that just gives me an opportunity to explain what I was saying earlier. I probably have seen it without remembering. I've never seen, as far as I can recall, purple or violet iron 3 solution. Every time I've seen iron 3 solution, it's been yellow. Remember that these iron 3 hexaaqua ions are pretty good acids. Okay, they're pretty good acids. So therefore, they're readily going to dissociate. We expect any weak acid to dissociate to a point, and for it to already be like that when we come to it. It doesn't start dissociating at some point, it's already done it. So when we look at a solution of iron 3 aqueous, just with the aqueous, just with this water, the surrounding water molecules, there'll have been some dissociation, which is also known as hydrolysis here. That's a term you'll see in your textbooks when you look. And so actually our iron 3 hexaaqua is more like this species, the one with 5 waters and 1 hydroxide, or this species with 4 and 2. And so there's a bit of yellow in there, there's a bit of the other yellow from the other species, there's a bit of the violet from the hexaaqua. You've got all 3, and so the colour mixes to make an overall yellowy colour. That purple's actually very bright. I had to doctor that picture to make it look a bit more purple. But as we said earlier, moving on now, the tris-hydroxy-tris-aqua complex, this precipitate, is the solid there, and it's orange or brown, or orange-brown, or rusty coloured. Okay, so that was iron 3 hexaaqua. Let's with hydroxide. Let's now consider iron 3 hexaaqua with ammonia. So what we said last time was that ammonia solution is alkaline, so there's hydroxide present, so you get a lot of the same reactions that you see with OH- as with NH3, and it's the same here. There's no ligand substitution. We saw, the only time we'll see ligand substitution, by the way, was back in copper 2, where we saw some an ammonia complex being formed. All we see with ammonia and iron 3 hexaaqua is the good old acid-base reaction that we've just talked about. However, this is something I could have mentioned last video, but I knew it would be a bit long, so I thought I'd save it for this one. However, ammonia is also a base, and when I say that, I mean a Lowry-Bronsted base, a H+ acceptor. So so that's the observation that happens. So rather than showing the plus ammonia reaction as with hydroxide as the Bronsted base accepting the hydrogen, we could show ammonia not acting as a ligand, not forming any kind of amine complex, but acting as a base and picking off those acidic hydrogens from the aqua complex. And we could write it as such. Hopefully you can see what's happened there. I've just swapped out one base for another. Hydroxide's been replaced by ammonia, and therefore water's been replaced by ammonium in the equation. And we could have done that for the copper 2+ and the iron 2+ hexaquas reacting with ammonia in the previous set of notes as well. We've just got a base in there, a Lowry-Bronsted base, accepting a H, and there are 2 bases, there's hydroxide and there's ammonia in ammonia solution. Anything that followed was ligand exchange, and as I said, it was only for copper where we actually see that, so we won't keep talking about ammonia ligands from this point onwards. So acid-base is all we get there. Either way, the transition metal complex is what you can see. So it's that violet to that rusty orange colour. The metal complex doesn't change there, it's just which base does the job of stripping it of its hydrogens. So there's no difference in the observation, however you balance that equation with ammonia or with hydroxide. So that takes us to aluminium hexaaqua. Like I said, we'll deal with carbonate for both afterwards because there's something special to say there. Aluminium is pretty predictable, so we can probably sort of speed run this a bit now, but I don't want to rush anything. So we see the same patterns as before. So how about this? You start now. We're going to write some equations for aluminium hexaaqua reacting with hydroxide and with ammonia. There is something special about its reaction with hydroxide. There's an extra step which we will need to deal with. But how about you pause, do it in rough, just scribble down a couple of equations, practice writing them with the charges, the square brackets, and then come back and listen to me as I go on, but double check as you go. So here we are. There is a really formulaic sort of thing now. Once you get past the complexity or the apparent complexity of all those brackets and square brackets and the rest of it, once you get past that, you can see what's going on here. Yet another aqua ligand complex turning into a hydroxy aqua ligand complex. It will take as many hydroxides as it has positive charges, and at that point it's ended up as an uncharged species, and at that point it's a precipitate. So we say that after that point, in all the examples so far, copper 2, iron 2 and iron 3, that's where the acid-base reaction stops, basically. Fine. So I've balanced that equation as such, and it's perfectly correct. Tick. However, aluminium is a bit of a wild card. Again, I just want to remind you it's not a transition metal. Observations. So we said at the start of this video that because it's not a transition metal, it's a colourless solution, and any solids that are formed are just going to be uncoloured as well, so white precipitates. True. Now, aluminium is a little bit different from the other examples we've had, in that it's amphoteric. All right, there's the observation for you. Sorry, I'm forgetting what order I put these slides on. So colourless solution, that could be anything. Let's assume it's aluminium hexaaqua, so aluminium sulfate or aluminium chloride in there. There we've got these fine white particles of some kind of solid, which is supposed to be aluminium, 3 waters, 3 hydroxides. I just said it, aluminium hydroxide is amphoteric. We can call this species, this solid species here, aluminium hydroxide. I suppose if you wanted a more thorough name, it'd be aluminium tris aqua tris hydroxy. That's alphabetical order A and H. But we also said in previous lesson, don't worry about the naming. It's amphoteric. One thing that all of these hydroxides can do, all the ones that we've drawn that have been solids and appeared as precipitates, they can take H plus back in. That goes without saying, I hope. All right, but we haven't said it yet, so now's the right time to. So we've taken it for granted that here we're taking alkalis coming along and pulling off H's. If I just dropped a couple of drops of HCl onto any of those solid precipitates, I'd push the reaction back again, because all acid-base reactions are reversible. So while we haven't seen this sort of equation before, we could have written iron 3 there, or copper with 4 waters and 2, or iron 2 with 4 waters and 2 hydroxides, and the right number of hydrogens just going back to the aqua. They can all do that because hydroxides are basic, aren't they? Yeah. But aluminium hydroxide here can go a step further in the alkaline direction as well. And that's what this reaction is. So here it comes. Have a look at that. Now, that's kind of like saying, well, why didn't we just write that in the first place? Why didn't we just go from hexaaqua aluminium plus 4 hydroxides makes that? Because that's basically what we're doing. We've added 3 hydroxides and we make this. Then a 4th hydroxide gets added and we get the tetrahydroxy aluminate complex. Again, hang on a minute, that rings a bell. We've met this tetrahydroxy aluminate complex before. It appeared in the periodicity topic when we looked at aluminium oxide acting as a base and taking basically in hydroxide and ending up as this. Have a look at your notes from periodicity. Aluminium compounds in general, anything that can act as an acid or a base, so any kind of oxide or hydroxide, they're amphoteric. Anyway, so yeah, we could have just written it plus 4 hydroxides makes this tetrahydroxy aluminate. However, that would be missing an important observation that you would have an opportunity to make if you were doing it in the lab. So I hope I'm not going too fast here. You might want to just pause and sit down for a minute longer, but also if you keep listening, this might clear things up a little bit. Observations we're going to talk about on the next slide anyway. So there it is in a slightly more sort of schematic way that might help you imagine what this might be like if you were doing it in the lab, which obviously normally you would be. We start with our hexaaqua aluminium 3 complex, which is just a colourless solution, as we've said. Add a little bit of hydroxide. It turns out that the amount you're adding is like a 3-to-1 molar ratio, because we're going to add 3 hydroxides to then turn our aluminium hexaaqua into aluminium 3 waters, 3 hydroxy, and so no charge. At that point, we'd see a white precipitate. You might also be having flashbacks at this point to GCSE analytical chemistry if you did this topic, because you did it then as well, but you wouldn't have looked at all the formulae. Then on addition of extra hydroxide, so excess hydroxide, this didn't happen for any of the other examples we saw with iron and copper, but then actually we get a tetrahydroxy complex. Now, some AQA mark schemes will show that as like 4 hydroxy and 2 waters, so it's still octahedral. However, the official line is that it's tetrahedral, so this is completely good and what you need for your notes and for your exams and such. I suppose we could probably use a similar argument to why it's tetrahedral to what we say about chloride. Chloride, we've got negative ions that repel each other, and so you don't get 6 of them all squeezed around. You get 4. Whatever the reason is, it's a tetrahedral species. I'm going to go back a slide in a minute. One last thing to say about the observation though. So a white precipitate forms from our colourless solution, but then on addition of excess hydroxide, that white precipitate redissolves back to, well, it's aluminium, so it can only be colourless solution. There's no colour in this of any interest. I've just gone back a slide then. So let's just take one last quick look at this before we keep pushing on. Hexaaqua does what it always does as far as we're concerned from all the other examples. And then what we said was something we hadn't actually thought about before on these lessons anyway, but the idea that if you added acid, you just push it back again. So add hydroxide to go to that way, add acid to push it back again. All of our solids can do that. But then here, extra hydroxide pushes it to somewhere a bit further than any of our iron 3, iron 2 or copper 2 could go. Moving on. So we saw that slide, so I'll move past it. So what about with ammonia? Well, there's nothing new here. We said exactly what we're about to say about iron 3. There's no ligand exchange between aluminium species and ammonia, so you don't get any like aluminium amine complexes. So all we've got here, yet again, is that good old acid-base reaction. We saw that one a minute ago, but also we could write it like that. We'd never write NH3 if we were adding NaOH, because there isn't any ammonia in sodium hydroxide. But if the alkaline solution in question is ammonia solution, then while it might form some deep blue complex with copper 2+, it doesn't with any of the others that we study. So you've just got the same acid-base reaction happening there. I just want to say one more thing though. Again, if I backtrack, I hope that you're not trying to write stuff down and I'm getting in your way. We just said about that tetrahydroxy complex forming there in excess alkali, but that was excess hydroxide. Back again we go. I'm not going to keep flicking the slides now. That wouldn't happen if we were adding excess ammonia. So adding excess sodium hydroxide would push this into the 4OH minus AlOH4 minus complex. Ammonia can't do that because it's not a strong enough base. Okay, let's assume that. So adding excess drops of ammonia solution to hexaaqua is probably just going to stop it at the precipitate. However, I'm sure the examiner would forgive you if you suggested that it was eventually got so alkaline that it pushed the acid-base equilibrium over to aluminium 4-hydroxy. I don't think we should worry about that too much, but just mentioning it. Pause if you need more time. Moving back on now. Observations, we've already talked about them. Colourless solution, it's a solid, so it's going to be a white precipitate, and then it redissolves if it can, but not there. Now, that takes us to the final instalment in this, and it's all about these metal 3 aqua ions coming with carbonate. Now, what we saw with copper 2 and iron 2 was straightforward. It just made FeCO3 or CuCO3. So it was just a simple sort of precipitation reaction, making an insoluble solid of copper carbonate or iron 2 carbonate. Doesn't work quite the same way with these metal 3 aquas though, because remember from our first lesson on this, the metal 3 aqua ligand complexes are more acidic. We talked about the charge to size ratio of the metal 3 ion and weakening the OH bonds and the rest of it. They're more acidic. They're actually so acidic that rather than form a complex, like a lattice, an ionic lattice with carbonate, these metal aqua ions will neutralize carbonate. And as we know from lower school, hopefully, and if not from acid bases earlier this year and last year, Carbonate is any carbonate goes with any acid, Larry Bronsted type, in that equation there. Carbonate plus 2H plus makes water and CO2. So these metal 3 aqua ions are basically just going to act like Larry Bronsted acids on the carbonate and zip it apart to make CO2 and water, rather than form a compound with it, iron carbonate or copper carbonate or alum. So that takes us to another interesting point then. There is no aluminium carbonate, not formed by this process anyway. And since pretty well all carbonates are formed from aqueous solution, I suggest that aluminium carbonate doesn't exist. Might be wrong on that, but I'm pretty sure I'm right. So you're going to do a bit of an equation writing task here. Metal 3 hexaaqua, you can consider it to be like a triprotic acid, a bit like H3PO4 then, only it's not phosphoric acid, it's aluminium or iron 3 hexaaqua. But you can consider it as an acid that's capable of donating 3 H pluses to a base, or 2 bases. Carbonate is dibasic, it will accept 2 H pluses, so there's a bit of a 2 H pluses, 3 H pluses thing to deal with here. What I want you to do is write an equation for iron 3 hexaaqua reacting with carbonate. You don't need to show what the positive ion on the carbonate is. It's probably sodium carbonate, but we're not interested in that now because it's a spectator. So pause the video, take your time, write an equation for that triprotic acid there, iron 3 hexaaqua, doing what it does, as we've seen in previous slides, when it acts as an acid, turning into what it does, in other words, with carbonate. Take your time over this. The idea is that once you've got a correct equation here, we can then just copy and paste that and change Fe for Al, and it's the same. So it's the pattern of behavior we really want. The second equation is the same as the first. Okay, take some time on that. I'm going to move on right now. Here we go. So hopefully you've actually done that. It's well worth practicing, because the good way to learn is by being able to work it out rather than just memorizing these things. What have we got? We've got our triprotic, we said, acid. So I'm just showing it there as like it could dissociate off 3 H pluses. They'd go to a base. Carbonate is dibasic, as we said just a second ago, so it will only take 2. So we can treat this a bit like how we'd approach a half equation with electrons. This obviously isn't redox, it's acid-base, but we could use the H plus in a similar way to what we do with electrons. 3 and 2, so double one, triple the other. And that gives you that equation there. So yeah, that's the reacting ratio. 2 hexaaqua iron 3 complexes would give out a total of 6 H pluses to bases. Those 6 H pluses could be accepted by 3 carbonates to form, as you can see there. So what would the observations be like then? Come on, try and do this off the top of your head now, because you've already got the colours of those iron species. What would it look like? And is there a secondary observation, like something else in addition to what we already talked about? Well, again, hopefully you don't need any more time. We've got that violet or purple hexaaqua iron 3 complex turning into, remember, it's the precipitate in that picture, it's the bit at the top, it's the solid orange-brown precipitate. CO2 has also been produced, so is water, but the water is just going to go into solution, and it's aqueous to begin with, so we won't detect the water. But the CO2, hopefully that stands out to you then. There's going to be effervescence here as well. And what will we say it looks like? Well, it's effervescence of a colourless gas. Obviously, most gases are colourless, but they're not all colourless, so just specify it's a colourless gas. So we'd have a violet solution gives an orange-brown precipitate and effervescence of a colourless gas. And there is the equation for it. It's just another acid-base reaction, but with an awkward-looking acid, because it's not a conventional, well, it is a Larry Bronsted H plus type acid, but it's not obviously one. It's not HCl or H2SO4. But that's all it is. It's just being aware of that. So aluminium then, there's no trick question here. Aluminium gives exactly the same thing. So I've gone ahead and done that, because I did say it's just copy and paste. We've got another triprotic acid, same formula of behavior here. So we get that ratio and we get those formulae. What observations will be made this time then? Again, if you want time to think, then take it. Well, we're going to have a colourless solution giving a precipitate, because this thing hasn't got a charge, and it's a non-transition metal, so it's a safe assumption that it's going to be a white precipitate. So there's our colourless solution gives white precipitate. Again, carbonate's not a strong enough base. There is hydroxide present in carbonate solution, because there's a little bit that comes off the water when that turns into hydrogen carbonate, but there's by no means enough hydroxide around to push this all the way over into tetrahydroxy, so we won't see any redissolving of the precipitate in theory. and you've got CO2 being produced. There is actually a complication with these, but I'll mention it. I'm not going to write it down. CO2 dissolves into water, makes carbonic acid, and pushes the equilibrium back again, and you end up with lots of stuff in solution. But whatever. So, colourless solution gives white precipitate and effervescence of a colourless gas. That sounds good to me. So that is the end of our visit through Metal 3, and therefore it takes us to the end of the course, the way that we've worked through it. Quick summary of those. Again, I've got a sheet for you. I'm going to show you those in a minute. So yeah, as we saw there was nothing to do with ammonia here other than to note that it's also a base, and so you could use it to balance the picking off of the hydrogens from your hexaquas when you make your metal complexes, your hydroxide complexes. Don't forget about the carbon dioxide that comes off the metal 3s. The metal 3s are more acidic than the metal 2 hexaquas, so they don't form carbonates, they don't form any precipitate with carbonate, they actually form bubbles with carbonate, and it's the hydroxide that's left behind. Similar for the aluminium, there was just that extra thing to say about excess hydroxide pushing the aluminium equilibrium even further, and you get this tetrahydroxyaluminate complex. Okay, so hopefully, that is everything now. That is truly the end. You're going to have access to this in my classroom, and just in case you're not in my classroom, if you're looking at this in future years or whatever, then that's where you'll find it. It's the AQA document for teachers, really, confirming what the colours are that they expect you to see. And it's not very colourful itself, but everything is there. That's absolutely everything you need. There used to be a lot more on this course, so you'll find lots of past papers and lots of older textbooks and older notes that have got copper and chromium and lots of really interesting things in. Sadly not on the course anymore. So keep it simple if what your main focus is just revising what you need to know. That's a similar thing that's come from chem sheets. You notice it's also got the chlorides at the bottom, which you do need to know about in one respect, because you need to know about like coordination number changing when chloro complexes are formed from aqua complexes and such. However, the colours of them, it's debatable if you need to know them for your exam. But there they are, and obviously you can see being colour coded. The only thing I want to point out here is that I've been calling the iron 3 hydroxide complex orange or orange brown or rusty. The examiner actually does call it brown as well, but if you ever see it in reality, it is an orange brown rusty colour. It looks a lot like rust, let's just put it like that. Okay, so that is everything. The last bit that we've just managed to tick off there was basically just to mention aluminium and iron 3, and a bit of a recap of the acidity which we mentioned. That's it. Well done, everybody. We made it.